nested sequence. Nested sequence. What is meant by nested sequence? Nested sequence. Nested sequence. Definition of nested sequence is a sequence of set. A sequence of the set. A sequence of the set A(n) is said to be nested sequence if an is subset of an here a1 is contains a2 contains a3 contains up to so on contains an which contains an plus 1 which contains up to so on. That is a2 contains in a1, a2 contains in a1, a3 contains in a2 and up to so on. In this way, if that is the set, suppose that here taking any one of the interval, okay, here suppose that taking any one of the interval nested sequence means suppose Sn is equal to 1 upon n, okay, 1 upon n, their elements are the sequence of the set an is said to be nested sequence if a1 is a2 is contained in a1, a3 is contained in a2, in this way, okay. So 1 upon n sequence is 1 by 2, 1 by 3 up to so on up to 0, okay. That is 1 upon n is contained in 0 to 1 this interval, okay. All the elements of 1 upon sequence 1 upon n are contained in close interval 0 to 1, okay. So suppose that this is a1 set, okay. Then a2 set, suppose that in real life, suppose that this is here 0 1, okay. Then here again division this, okay, here dividing, then 1 upon n or 1 by 2 suppose that, okay, and here any something number, okay. So dividing this close interval 0 1 which contains interval, then 1 by 2 and here take a something any number, suppose that here 1 by 3 and here 1 by 2, okay. Then 1 by 2 1 by 3, okay. Then again taking one number, okay, in this way. So 0 1 this one interval, suppose that which is a1, then second interval this and this interval, okay. This is suppose that a2, then this is suppose that a3, this is suppose that a4 and up to so on. In this way, if interval are exist, then we say that given sequence is nested sequence, okay. So theorems on this interval theorem, nested interval theorem, okay. Nested interval theorem. Nested interval theorem statement is, this is very simple theorem. Let interval in, let interval in is an bn, let interval in is an bn, be a non-empty be a non-empty closed, this is non-empty closed bounded interval. A and B is a closed and also bounded interval of real number such that first one is given that I1 first interval A1 B1 is I1 is contains A2 contains I3, and in this way up to so on In, then In plus 1, that is In plus 1 is contained in In, then which is contained in In minus 1 up to so on I3 is contained in I2 up to so on I2 is contained in I1. Okay, in this way here exists. And second is given that limit n tends to infinity bn minus en is equal to limit n tends to infinity length of in is equal to 0. That is here given that at limit n tends to infinity length of in is 0 is given. Then what to prove here? Intersection of in where n runs from 1 to infinity contains precisely one element, precisely 1 point or 1 element. Okay, so how to prove? Here given that I1 interval contains I2, then I2 interval contains I3, and up to so on. This is given. In is interval given that I1 is interval given that A and Bn. Okay, and which is this interval is also closed interval and which is also bounded. Okay, bounded below by An and bounded above by Bn. Okay, and this one first and second are given. First is I1 interval contains I2 contains I3 in this way. Okay, and second is given that limit n tends to infinity, that is length of this interval bn minus en means length of given interval bn minus en is equal to limit n tends to infinity length of in is equal to 0 is given. And here to show that intersection of in contains precisely one point. Precisely one point means which contains only one point in given interval. Okay, so proof of this theorem. How to prove this theorem? Since any n belongs to set of positive integer I, then suppose that here interval, I am taking here interval. Okay, with this interval is given that set of real numbers. Okay, in this way, suppose here A1, this is B1. Okay, this first interval I1. Okay, and in is equal to an bn given that, and in is equal to an bn. Then if we taking 1, then a1 b1. Okay, then if we taking n is equal to 2, then I2 is contained in I1. So this is in this way, this is A2 and this is B2. Okay, so in this way, then if we taking n is equal to 3, then interval is A3 B3, so which is also containing A2, this is B3, and up to so on in this way, here something in bn, then here an plus 1, then bn plus 1 and up to so on in this way. Okay, so here let here in is equal to what is given, an bn b non-empty, in bn is any non-empty close and bounded interval. Okay, therefore I1 is equal to a1 and b1. Okay, this a1 b1 interval is I1 interval, these two, this is I1. Okay, then for second, this is I2 interval is a2 b2, and in this way up to so on in is an bn. Okay, so this is an bn, and in this way we taking a interval an plus 1 bn plus 1 and up to so on. Okay, so here hypothesis is given that here a1 b1 then a2 b2 up to so on. Okay, in this way. So here hypothesis, what says hypothesis is given that first hypothesis I1 contains I2 which contains I3 and up to so on. And here also clearly see that here I1 is contains I2 contains I3, and in this way here also exist. Okay, which imply that from this clearly we see that a1 is must be less than or equal to a2. Okay, which is must be less than or equal to a3. Okay, a1 is must be less than or equal to a2, which is less than or equal to a3. Okay, so if we taking any interval, suppose this is -2 to 3. Okay, then -2, then here -1, then here 0, then here 1 and up to so on in this way. Okay, so suppose that this is a1, then a1 this is a2. Okay, then if a1 is must be less equal a2, here -2 is strictly less than a2, but when interval is or these points are not known, then a1 is less equal to a2, then less equal a3 and up to so on in this way up to an is less equal am plus 1. Okay, and also from this interval here left to right, here right to left, here also given that b1 is strictly greater equal b2, because here suppose that 3, then 3 is strictly greater than here 2. Okay, then which is greater than or equal to 1, then which is greater than or equal to 0, then 0 is greater than or equal to -1 and up to so on in this way. So here b1 is must be greater equal, b2 is greater equal b3, which is greater equal and up to so on in this way. Okay, then here clearly here a1 is less equal a2 is less equal up to so on, and this is b1 up to b2, b2 is greater equal b1 is greater equal b2 is greater equal b3 up to so on, which is greater equal, suppose that bn then greater equal bn plus 1 up to so on. So here sequence an, this sequence an is increasing sequence. Okay, this sequence an is increasing sequence, that is non decreasing. Okay, this is increasing sequence, and which is bounded above by last point. Here last point is in this way, if we taking a1 a2 up to so on, their last point is must be bn. Okay, their last point here, if we taking, suppose that if we taking any interval in this way, here suppose that a1 then a2 up to so on, their last point is here must be b1 point, sorry, not bn, b1 point. Okay, then a3 up to so on. Okay, in this way, this which is bounded above by b1, and similarly b1 b2 second sequence, b1 bn sequence, which is, this sequence is decreasing sequence, and this decreasing sequence is bounded below by a1. Okay, this sequence is bounded below by a1, which is bounded by b1, and sequence bn, which is this decreasing sequence, and this is bounded below. Okay, this is bounded above and this is bounded below by a1. Okay, bounded below by a1 and bounded below by a1. Therefore if result is here, if sequence Sn is increasing sequence and bounded above, then which is convergent sequence. Okay, and sequence Sn is decreasing sequence and bounded below, then which is also convergent. So using this, here sequence an is increasing sequence and this is bounded above, therefore which is also convergent, and sequence bn is also decreasing sequence which is bounded below, and this is also which implies that convergent. Okay, this also convergent, that is sequence an has limit exist and sequence bn has also limit exist. Okay, so here, so therefore limit n tends to infinity, an has limit, suppose that sequence an is convergent, which implies that which has any limit, suppose that x. Okay, and sequence bn has limit is, suppose that y. Okay, suppose that y, and therefore by hypothesis, given hypothesis second hypothesis of our theorem is, what is second hypothesis? Here limit n tends to infinity bn minus an, limit n tends to infinity bn minus an is equal to 0, given that. Okay, here bn minus an is equal to 0 is given, and so therefore taking limit separately, n tends to infinity bn minus limit n tends to infinity an is equal to, but their limit is y minus x is equal to 0, which implies that y is equal to x, that is sequence an has a1, sequence an and sequence bn has same limit, and this same limit is, suppose that which has take any one number. Okay, suppose that y is equal to x is, suppose that which is z. Okay, so an and bn has same limit, and therefore sequence an is increasing sequence and which is convergent, and it has limit is z, which implies that which is increasing sequence and it is convergent, and convergent converges to z. Okay, converges to z, which implies that z is a must be least upper bound of given sequence an. Z is a must be least upper bound of given sequence an, and also bn sequence is decreasing sequence, and which is convergent, and convergent to, suppose that this convergent to z, which implies that from this sequence decreasing sequence and convergent to z, which implies that z is a greatest lower bound of Bn, greatest lower bound of Bn. Okay, therefore Z An has least upper bound is Z and Bn has greatest lower bound is Z. That is An is less equal Z and Bn is greater equal Z. Okay, An is less equal Z and Bn is greater equal Z, and therefore An, therefore in this interval Z is value of Z is lies in between An is less equal Z and Z is less equal Bn. That is Z is lies in between interval An and Bn. Okay, interval An and Bn, and therefore An and Bn interval An is must less equal n minus 1, which is less equal n minus 2 up to so on, which is less equal a2 less equal a1. Okay, and which is less equal Bn is greater equal Bn is less equal Bn minus 1 up to so on, lastly which is less than B1. Okay, in this way Z is lies in between intersection of all these intervals, in, intersection of all these intervals. Okay, that is Z is also lies in between A1 B1, Z is also lies in between A2 B2 up to so on, Z is also lies in between A and Bn, which imply that Z is lies in between intersection of all these intervals In. That is Z belongs to intersection of In. Okay, this is first prop. Okay, then now to show intersection of In contains precisely one point. Okay, now we have to show this intersection of In is non-empty. Here Z belongs to intersection of In. This prove, okay, that is this intersection is non-empty, and now we have to prove intersection of In contains only one point. Okay, so they are proved by contradiction. Suppose which contains 2 points. Suppose that Z and Z dash, these 2 points are belongs to in given intersection of intervals In. Okay, and Z is not equal to Z dash. Okay, Z is not equal to Z dash. That is Z dash minus Z is equal to Z. Their subtraction is must be greater than 0, because Z is not equal to Z dash. Okay, Z and Z dash are not same element. So this is different element, then their subtraction or their distance between these 2 points is must be greater than 0. Okay, that is any two points from this, their distance, any 2 points of given interval n, their distance is not here Z and Z dash is not equal to 0, not equal, then their distance is must be greater than 0. Okay, but our hypothesis says that limit n tends to infinity length of In means length of given interval, that is any two interval. If it, taking any 2 points of given interval, then their distance is 0. Okay, but here Z dash and Z are 2 different elements and their distance is greater than 0, and this is contradiction to our hypothesis. Hypothesis is length of In is equal to 0, and therefore intersection of In, our assumption is intersection of I is contain 2 elements. This assumption is must be wrong. Okay, and therefore which contains precisely 1 point. Okay, so proof of this. Here Im plus 1 is equal to interval given that Am plus 1 Bm plus 1. In this way, since by hypothesis here given that since by hypothesis first hypothesis. Given first hypothesis is A1 contains A2, contains A3 up to so on, contains IN plus 1 and up to so on. In this way, which imply that here, which imply that I1, which imply that A1 is must be less equal A2 is must be less equal A3, okay, which is up to so on, which is less equal up to so on, less equal an plus 1 and up to so on, okay. In this way, this sequence is given that, and B1 is greater equal B2 is greater equal B3 is greater equal up to so on, Bn is greater equal Bn plus 1 is greater equal up to so on. In this way, okay. So therefore that is sequence an, this sequence an is increasing sequence or non-decreasing sequence, is non-decreasing sequence, and which is bounded above by what point? B1 point, okay, which is bounded above by B1, and sequence Bn, second sequence is Bn is non-increasing sequence, that is this is decreasing sequence, non-increasing sequence, and which is bounded below by A1, okay, which is bounded below by A1, and therefore by using result, any sequence is any non-decreasing sequence and bounded above is convergent, and non-increasing sequence and bounded below is convergent. Therefore sequence An and sequence Bn is convergent, okay, is convergent. Therefore this is convergent, which implies that it has limit n tends to infinity. An is equal to suppose that L, and or here take X, okay, and limit n tends to infinity. Sequence Bn has limit, suppose that Y, okay, suppose that Y, but our second hypothesis is what is say? Second hypothesis is, but by hypothesis second what say? Limit n tends to infinity, Bn minus An is equal to 0, and therefore taking limit separately, Bn minus limit n tends to infinity, An equal to 0, and therefore their limit is x minus y equal to 0, which implies that x is equal to y. That is sequence An and sequence Bn has same limit, okay. So take their value something L or Z, okay. Suppose that is x is equal to y is equal to, take Z, okay, say Z, okay. And therefore given sequence An is increasing sequence and bounded above, and sequence Bn is decreasing sequence and bounded below, and which has same limit Z. Therefore for this sequence for An sequence, Z is least upper bound of the sequence An, and greatest lower bound of the sequence of the sequence Bn. Okay, of the sequence Bn, and that is all terms of sequence A and R must be less than or equal to Z, and all terms of sequence B and R must be greater than or equal to Z, and therefore Z lies in between ZR lies in between A and Bn, and therefore Z is must be belongs to intersection of intervals In. Okay, where n runs from 1 to infinity. Okay, now this is one part. Then now to show what to show. Intersection of ion contains precisely one point, or only contains only one point. Okay, contains only one point. So proof by contradiction. If possible suppose which contains 2 points. Okay, if possible suppose Z dash belongs to intersection of ion where n runs from 1 to infinity, and Z dash is not equal to Z, that is which contain, if possible suppose intersection of ion contains two points Z and Z dash, that is Z dash belongs to intersection of ion and Z dash is not equal to Z, and therefore Z dash minus Z, their distance is must be greater than 0, which imply that limit n tends to infinity, Z dash minus Z is must be greater than 0, but or which imply that limit n tends to infinity, length of 2 point is must be greater than 0, that is length of ion is greater than 0, and which is contradiction to hypothesis second. Okay, hypothesis second, and therefore our assumption, this assumption is wrong, and therefore limit n tends to infinity Bn minus An. Hypothesis second is Bn minus An is equal to limit n tends to infinity, length of ion is equal to 0, and therefore our assumption was wrong. Okay, and therefore intersection of ion contains only one point. Intersection of ion contains only one point, or precisely one point. Okay, or here take precisely. Okay, precisely one point. This is a proof of our theorem.